Hi, my name is Max Wetherington, and today I'm going to be talking with you about basic machine learning approaches to simplify image analysis. Before we begin, I just want to preface with saying that I'm not a computer scientist. One of the main messages of this presentation is that it's not necessary for you to have knowledge in computer science or machine learning in order to use these user-friendly tools for image analysis. Some of you have maybe heard this age-old question of how many jelly beans are in a jar, or count how many M&Ms are in the jar. This is typically, one of your geometry class questions where you then measure the size of the jar to guess the amount of beans that are present. But if you don't have the ability to measure that, or maybe let's say there's many jars and just way too many things to count, or maybe you need a particular physical property of some of those beans that you want to extract. The ways that we do this within the world of image analysis is through computer vision and image classification via machine learning. Is a very powerful tool for what are seemingly intractable image analysis problems. So there are two general types of machine learning. There's supervised machine learning and unsupervised. In supervised machine learning, your input data is labeled, and in unsupervised, the input data is unlabeled. And generally, when we're using supervised machine learning, we're using this to help categorize and predict our data sets. Whereas, a very popular subject right now is unsupervised machine learning, where AI is used to help either in pattern recognition or pattern generation. So in this talk, we're looking at supervised machine learning, where we provide the input data. An example of supervised machine learning is this WEKA software, Waikato Environment for Knowledge Analysis, which is a GUI-based machine learning that leverages Java language. And on our right, we have ImageJ, which is also found in prepackaged software called FIJI, which just includes all the plugins that come along with ImageJ. And in 2017, these two programs, the machine learning of WEKA and the image analysis of ImageJ, were combined to make a very user-friendly interface that's open source. And you really don't have to be an expert in computer science to apply the tools that are built into WEKA to then perform image analysis on your samples. This tool, this trainable WEKA segmentation tool, was first brought to my attention by Bevan Harbinson, who was an undergrad fellow in our MRI, Materials Research Institute undergraduate fellowship program. And he used this initially as a tool to help with particle size analysis of microplastics, but then he built a video catalog for us referencing particular applications of WEKA. And here I have a QR code that links you to one of the videos that he's previously recorded on how to use WEKA inside of FIJI. And this graphic here comes from that original paper explaining some of the classification that is then required that's done actually by the user. We train the data set. Again, this is a supervised machine learning process. And that training is then built into a classifier that's used to an image or a set of images to identify a particular feature. One application of using ImageJ and WEKA is in this project within the Robinson Group, performed by Joe Laura and Ricardo Torsi, where their goal was to grow a coalesced monolayer film of MOS2 via MOCVD. And one method that we use to determine coalescence of a monolayer is through AFM, atomic force microscopy, where we can use both the height channel of the film that's grown and the adhesion channel to determine the number of layers and the coverage. So in the height channel, there's a little bit of a challenge because the material is grown on a sapphire substrate, which has some terrace structure to it. And then superimposed on top of that is the monolayer that's grown from the MOS2. And that can be difficult to determine the continuity of that film, but sometimes is a good way for us to determine multiple layers. So we use the adhesion channel to help identify the coalescence of the monolayer film, where we see a pretty nice contrast between the adhesion of the AFM probe on the sapphire substrate versus on the MOS2 film. One of the challenges, though, is sometimes we see that the adhesion channel may not have easily interpretable differences in the contrast between the MOS2 regions and the sapphire regions, maybe because the tip picked up some debris, or there just might have been a slight change in your feedback of the AFM, which can change the background color of the overall scan. And this is where WEKA image analysis helps, and I'm going to give a demonstration of that right now. So I'm going to provide a quick overview of FIJI. So first you got to download the executable, as I mentioned, and I provided that QR code. Once you open it the first time, it might take a minute just to install all the plugins. And then once it's open, you can just drag a file over into this little taskbar below. First thing we're going to do is we're going to crop the image, and I'll just select the area. Oh, first I need to actually select a region. So I have these different tools here, so we'll just use that rectangular tool. I'll draw this area out right here, and we can go into image and crop. So now what we'll do is we want to turn this into an 8-bit image, and we can load this in the, under plugins, the segmentation and the trainable WEKA segmentation tool. So now it's going to load that image into our trainable segmentation tool. What I'm going to do is I'm going to draw regions around features of interest, and then define that to a particular class. So you can use this freehand tool, and I can just kind of draw in like this triangle is one region of interest. And really, this is where you want to do your best to kind of draw in as much of an area as you can with varying kinds of backgrounds. So you see here, there's like a little white streak that goes across this image. Possibly, something might have changed in the feedback of the AFM as it was scanning, but you want to make sure you kind of capture these different types of backgrounds, and then it will do a better job in segmenting this out. So I might want to collect one kind of near the edge here. And now I also want to classify the substrate, and if I just do Control plus here, or you can use the magnifying lens and just go in, and we can draw in this region, and we'll define that as a class. I can draw in this region. Ooh, caught some of that edge, so I don't want that. So one thing that's unfortunate is there's no undo button in this, but if you just draw another region, it will redo. So let's go in over here. So it'll actually remove that previous drawing that I had, and I'll just select this, and we can add that. If you want, you can go under settings and actually label these classes. So we can say the first class is MOS2, the second class is, we'll just call it substrate, and we hit OK. And right here, if you want, you could add more classes, and to my knowledge there's really no limit to the number of classes that you can add. So now what we'll go ahead and do is we'll click this Train Classifier button, and let's see how it does. I want to zoom back out. And it did a pretty good job. Now it missed some of these boundaries here, and so what we could do is we can just keep iterating through this process. So I could remove this overlay. I toggle the overlay here, and maybe I just want to draw a line right here to define this boundary. And add that to the substrate, and I'll just kind of draw this little line right here. And let's try to train that again and see how that does. A little bit better. And so as you go through this, you can just kind of improve the classes here by just kind of accounting for any of these anomalies, either along the edge or where it doesn't clearly see that this is a grain that's separated. We can help the tool out, and just it continues to learn. You can actually save this classifier to a folder and then apply it to every image that's in that folder. But in this case now, I'm going to go ahead and we already trained the classifier, so now I'll go ahead and create result. And we have our binary image here. Now, you could again turn this into an 8-bit, and it is 8-bit. Now it's grayscale, and you can threshold this. Image, adjust, and threshold. We now see that we've segmented this out and apply that. And you will then get your result here. And then once you have that thresholded image, you can go into Analyze and Analyze Particles. And we can provide a summary of everything. If you don't want to include, maybe if there's just like 1 or 2 pixels, you can define the size of the pixels here. So 0 to infinity is all-inclusive. You could maybe say anything that's greater than 5 pixels to infinity. You can define the circularity of the particles. You can exclude things on the edge, which in this case I might, because we didn't optimize that along this right edge here. And hit OK. So you'll notice this is actually a different screen. When I first hit Get Results, or OK, in this Analyze Particles window, the pixel units was not selected, so the units were in inches squared. So when I set this to 5, that was 5 inches squared, which every particle was much smaller than that. So if you select pixel units, you'll notice I actually get results now. And in this summary table, it shows you the percentage of the area of the particles here. So this, in this case, is the percentage of the substrate that was exposed. So we're close to 95% area coverage of that monolayer. And here you can extract all this data from the this results table if you wanted to do more analytics on the size, distribution. But in this case, what we really just cared about is the percent coverage. So using that method that I just showed you in WEKA, we then applied that to every AFM scanned sample that Joe and Ricardo grew, and they used the process parameters from the growth, and then we have now a feedback from the AFM characterization where we can quantify, what the actual overlayer growth is and the number of layers that have grown. So the coverage and the number of layers. And then also this provides an opportunity to correlate this to maybe changes in a furnace. This is really beneficial because this provides a little bit of a longevity in a research group where there is turnover from one grad student to the next after a few years, and some of that information, that historical information, either correlated to the furnace or the growth mechanism or growth parameters, can be lost. So now iterating through many growths, Joe has now gotten to a point where we're nearly getting to a perfectly coalesced monolayer film that is only monolayer, which was the goal. Another example where we leverage the WEKA ImageJ program is another two-dimensional material that is a 2D polar metal grown at the interface of graphene and silicon carbide. It actually intercalates between those layers, and one thing that we've discovered is that the metals that form between these layers can have different phases. There's a very limited number of approaches, characterization approaches, that enables us to determine those phases. And so using correlative analysis between Raman, Auger, and optical microscopy, we are able to differentiate those phases in Raman and Auger, and then now we can use the optical micrograph which is a much faster approach to assess the intercalation process and differentiate the phases, and we can characterize that and segment that data out with the WEKA segmentation tool, and allows us to look over a much larger area of the substrate that we've grown and provide a more statistically meaningful quantification of the coverage and uniformity at wafer scale. And so this is what it looks like when, in this case, we have 3 different classes of features within the image. And as I mentioned, we can classify more than 3. I don't know what the limit is, but you can go much greater than 3. And now we have these probability maps for each of those unique classes that we've defined within the WEKA software. So once you have your image segmented into classes of interest to you, now there's all sorts of other opportunities within the ImageJ analysis program that are plugins that have been built by other users or companies, and you can apply. In this case, I'm demonstrating some morphological profiling parameters that you can extract from images. And another one that was highlighted by another MRI staff member here, Wes Auker, shows that when you have fibers in an SEM image, you can use the Orientation J plugin to actually extract the vectors of that particular fiber within the image itself. So these are, really cool other fun image analysis techniques that you can then apply to your segmented data. I'll just lastly point out that, as I mentioned, this is a user-friendly tool. You can certainly dig into the tool itself, just as probably most drivers don't know how to rebuild their engine in their car. You are probably an okay driver, but when using this tool, you don't necessarily need to know the inner workings of every single function. Of course, it helps. It helps to know how your engine's built. If you have a catastrophic failure, beneficial to know how to fix that. However, it's not required. So the point being is changing these parameters can make very subtle difference in the end results. The biggest source of error is likely how good of a job you do in drawing your classifications and whether or not you falsely classify or label a particular feature to a particular class. And that's it. So thank you so much for listening, and hope you have a great day.